maybe it's the weather, and I guess it's cold, but it's snowing or anything. But, all right. We just increased the size quite a bit, that's good. So,
I'm sorry.
we're doing, project. So we're doing, project 1, part 2. Spring sorting gauge, part 2. And in D2L, again, we only have, the Word document, there's no files to download. There will be coming up, like the next one. There's a screw, a socket head cap screw that's kind of a generic size. We're gonna bring that in, and I'll show you when I do a little down here. We're gonna use it 6 places, and we're going to adjust the size of it. And, stuff like that. For this session, it's just a Word document. All you're doing is, last week we created springs, created separate files. This week we're going to create, not everything you see on the screen there. That's actually, most of that's the following assignment. But we're going to make that plate on the bottom. The plate's got some holes in it for screws. You can actually see the screws right there. That's a socket head cap screw there. So we're going to have to adjust the correct size. We're going to talk about all this stuff next time, but there's formulas for how much of the screw actually engages with whatever it's going into, in this case, this plate, right? The length, that's called the thread engagement right there. We're gonna have a little formula for that, based on the diameter of the screw, the length of the screw that's not engaged for the threading, that's related to how much thread engagement there is, and so on. So there's all these little formulas we're gonna be using to do all this. And even, again, I don't wanna jump ahead too far, but once we figure that out, which screw we're gonna use, then, we're gonna make these blocks, and the blocks are held down with these screws. That's a counterbore hole, right? There's a large cylinder here that the screw just drops right into, and then it stops here, and it gets threaded into the plate on the bottom. Even the length of that counterbore cylinder, then we gotta calculate that. Because, there's so much thread, so much of the screw up here, and then the rest of the part is the height. You gotta calculate all that. So there's all these little calculations we're gonna make. They're not real complex math or anything. You'll see it's pretty straightforward. But, so that's what we're gonna be doing in a while. I'll hide these things. This is what one of the things we're gonna make today. In fact, that's what we're gonna design that today, build that in CAD. Plus, we're gonna make this assembly, all right? So, the little discussion, pretty much this class, there's gonna be little discussions about tooling and materials and other things like that. This week, it's really just about NX, looking at assemblies. We've done it in previous classes. We did a little bit in NX1 if you took that class. If you took NX2, we did it a little bit more formally. We worked with assemblies there. If you did the upper body and the underbody, we worked with assemblies there too. But, we're as one of the first projects in this class, I'm going to talk about it a little bit as we're doing it, sort of as a refresher, if you haven't done it in a while. So we're going to talk about the way NX, because ultimately this is a CAD class. Right? This tool and die class is a CAD class for tool and die. So yes, it's related to the actual tools and how you work with them and all the things about the tools, but it's also related to how we show that and represent that in NX. And I really don't mean it to be just NX. I could have made this exact same class in CATIA or SolidWorks or Solid Edge or lots of different softwares. It's really more about using CAD in general, not just NX. But since we are using NX, of course we got to talk a little bit about it. So I'm going to turn that on or get rid of that for right now. And I'll go through some of it, kind of like you're going to do in the exercise. I might not do every single step in the exercise, but I'll call out what you're going to do. It's all written in my typical document where every step is there. So the first thing we're going to do is build the assembly. So let me pull it up again real quick. The assembly, you know, here's the top branch, that's the assembly, it's got ASM in it, and then we're gonna make, the parts, just these first four parts, four components, they all have MDL, it's kind of a representation of model. We're gonna name that, but that's what those are. We're not gonna do the cap screws until next week. We're not gonna bring the springs in really until next week either, because, or maybe even the week after that. So, for today, when I'm done, you'll have this assembly and these four parts, okay? But only one of the parts will actually have geometry. You can build an assembly with empty parts, that's what we're starting out. Okay? So we're gonna build an assembly with empty parts, and then one of the parts will make that plate, okay? So, this will go kind of fast. This document is 9 pages. I know the document that we're gonna create the entire assembly and create all the blocks and line everything up exactly correctly and make some drawings. It's like a 30-page document, Word document, so it seems like, man, it's gonna take a long time. But it's one of those where each page has maybe a couple of sentences with pictures on it, and they go quicker. It takes me a long time to create those and make all the pictures, and it takes a lot of space on the document. But doing the assignment isn't anywhere near as long as you think. It's a 30-page document, but it's still not gonna be a long exercise. Well, we'll see. So anyway, we're starting with what we're gonna do today. We're gonna build an assembly, an NX, okay? There's a naming convention we're gonna use. I guess I can show that. And the person who did this class previously, he was from GM, and he was using actual GM part numbering and things like that. And we're really not supposed to do that. We're not supposed to use, not that it's secret, but they call it proprietary. We're not supposed to do things exactly like another company would do. So we're kind of following the same concept. We're gonna name things. For example, this project we're working on, we're gonna name it Project 1000. Okay, this is Project 1, this is spring sorting gauge. It's Project 1000. So the assembly, the name is 1000.asm, and we're not really gonna do any revisions of this, but if we were to create this assembly and release it, meaning yes, it's official, the company's accepting it the way it is, and then some changes would come along, well, we might make another revision of that same part. So that 01 in the end, if we release this, then we're not really actually gonna go back and modify the same one. We're gonna start with that, but then make a new one, and it'll be revision 2, all right? So this first one, again, Project 1000.asm for this is the assembly branch. .01 is the first revision, right? Then each part is gonna have its own part number. So there's a plate and there's 3 blocks. Right? We're gonna make the plate today, or I'll talk about the blocks a little bit, but not too much. We're just gonna make empty models. So there's a place to put them when we do create it, which is next one. Okay? But those are different part numbers. We can't have it as a 1000 because that's the assembly part number. So the plate's gonna be 1001. First block will be 1002, then there's 1003, 1004. They're all revision 1. And we put an MDL there, and actually that's kind of the way GM did it too. If it was an assembly, they put ASM in the part number. If it was an individual component part, they put MDL in there, or something like that, right? So that's what we're gonna build, right? We're just building that in NX, really nothing to do with tooling or anything. So first thing I'll do, I'll just do it. I'm gonna go to File New. And yes, we have these templates in NX, right? There's all these tabs along the top. We're not doing drawings. We're gonna do those later. Right now we're doing what they call model type templates. And inside the model type templates, these are really the templates. There's a model type, there's an assembly type, there's these other ones, Shape Studio, Sheet Metal, and so on. Not to get into all those. We're gonna be dealing with modeling, or model and assembly. I wish it said component and assembly, because everything could be a model. Model is a more generic term, but assembly means a group of parts, and a component means something that's one of the parts in an assembly. But anyway, they call it model. The first one I'm gonna make is the assembly. And again, it's gonna be that 1000.asm, right? So I go to assembly template. We're doing everything in NX in millimeters, but we're acting like, a lot of shops, a lot of machine shops, a lot of drawings and whatnot, manufacturing, they're all inches. We're gonna build it, converting it from the inches that we know we're gonna use into a millimeter model. And it's actually real easy to do. with most software included, you can actually see. But anyways, make sure it's millimeters, call it an assembly. Down here for the name, like I said, it's gonna be 1000.ASM. .01. Okay, that's the name of it. Put it in a folder, set up a folder on your machine or on your thumb drive, whatever, where you can put things. I made one for this class for this semester, winter 25. Actually, I have tool-and-die project one, when I had nothing in there yet. So I made this thing called tool-and-die project one. So I'm gonna hit OK. Remember, just putting a folder down there and actually even hitting OK like this, that doesn't save that. It's not saved. Just because I gave it a folder, I created it, and if I just hit the save button now, it knows where to put it. If you don't give it a valid folder, though, the first time you save it, it'll bring up a little window that says, you probably need to tell it where you're going to save it, right? But anyway, just so you know, it doesn't save it automatically. Because I created a brand new assembly, there's a workflow. When you use the assembly template, it thinks you want to immediately add component parts into it, add existing parts. So it brings up this assemble thing. We don't want to add anything that's already existing. Ultimately, I'm going to put those springs in here, but right now I'm just building the kind of like the skeleton assembly. It's just parts, like the main parts. But we're going to do that. So I don't want to add anything right now. You can ignore this. You can just hit cancel. So I'm in a new part. It's an assembly. Well, the only reason it's an assembly, I say that, is because I put ASM in the name, part number, and I use the assembly template. But I'm going to say this again, just so you're aware of this. In NX, it actually is just a single component right now. That's what it thinks of itself as. It's a single cube right there, right? I could have made this exact same thing using the model template. The only difference with the model template is it also creates a CSIS in the middle. That's the WCS, which we're not going to use. Remember that guy, we hit the WT, it's a toggle. Okay, I'm going to turn that off just because I don't want to see it. But there's my first file, it's an assembly file. Then I'm going to add it, and it tells you this in the instructions. It says, well, let me show you something. It tells you to go to the preferences, okay? Because what I want to do is create a new child in here. As I'm creating it, this is called the top-down method. Create a new assembly and all the new parts, all at the same time. Bottom up would mean I create the assembly, but the parts are already made somewhere else, and I just add them. We're creating them brand new. So normally you would go to assemblies, and you go to new components. If this is bold, that means it's the work part, it's active. So if I create a new component right now, component, remember what I said, it means it's a child. So that button, what it's going to attempt to do is add a new child to that. Underneath it, it'll be indented over. Of course, if I do it right now, because my software was loaded the way it was loaded, and there's certain settings, there's certain defaults, it comes up with a new component window like this. I've never used this, and I don't know if any companies use it. It's not what we're used to using. What we usually do when we want to create a new component in this assembly, I want to go to that, I want the file new window to pop up. You might remember this from classes they just had if you were in my upper body. This one doesn't let me, it says component name, but it's actually not what you think. It's not the part number. And it doesn't let me pick a folder where this new one's going to go. In other words, I don't want this window. That's not what I really wanted. Okay? So I'm going to cancel this. What we really want is the file new window. And usually, or it used to, in NX11 it would come up, if I went to new component, that would come up automatically, file new, and you pick a model, and you give it a name and a folder, and it would stick it under here when you're done. But obviously it's changed in this newer version of NX. Well, there's different ways of adding components. That is, I guess it's a newer way of doing it, and maybe they're trying to push that way eventually, but we're gonna do it the old way. We're gonna make it like we did before. So in order to do that, I don't want to do new component right now. First, I'm going to go to File, Preferences, Assemblies, okay? And there's different items here in Assemblies, and there's one called Component. So what this window's about here is, well, when you're working with assemblies and you want to deal with components, children, here's some stuff I can set for that. And right here, it says New Component, which is that command I was trying to use.
This is where you define, well, how do you wanna create a new component? And it's set to model by default, which is that one that we saw, which I don't want. Go behind here. I wanna select the new component from file new. In other words, I wanna create a new one, but also give it a name and give it a folder. You should only have to do this, well, let me think about that. I said it. Actually, I think if I make another assembly and I do it again, I'm gonna have to change it. I think, I don't remember now if I do it again. I'll test it a little bit again. And just as an FYI, some of these settings, if you go to utilities, customer defaults, I talked about this. This is the base defaults for everything. And in here somewhere, I could probably change that. I know I could because I found it before. I could go to assemblies and somewhere in there, component operations. See, it says component, command to use in file new. Oh, let's put it on that side. That's a slightly different. But there is one on here somewhere where I could say, well, when I go to new component, go to file new. There is one in here to say that. But anyway, it didn't say that. But I went to the preferences and I changed it. Now if I go to new component, see, it goes to the file new. So anybody that hasn't seen NX since we were in NX 11, this is what you might remember. Okay. So I'm making the first part. You see, it's taking me a long time because I'm explaining it. If you're doing the instructions, it might have taken you a minute or two to do this, right? This new one's gonna be a model type. And this is the first part, so I'm gonna call it 1001.mdl.01. Okay, 100.mdl.01. And this one, now the folder on here, it should be pointing at the same folder I was at just a second ago. Yeah, it's my winter 25 tool and die project folder. So that's good. So I'm gonna hit OK. That way, it will go to that folder, and it'll have the same name I just gave it. You'll see it pop up here in a second. See, now this window came back up, and see it plugged it in there, but it went to the file new window first. And this window, again, I never really use it for what it's really intended. It's one of those, if you're creating an assembly of parts and you open up, maybe you were given a bunch of parts all in one model, and it's on the screen right now, you can pick individual pieces and say, well, this part I'm about to finish, 1.100.1001, I want this part in, the solid. Well, there isn't anything to select, so I'm just gonna, it says select object, I'm not gonna select anything, I'm just gonna hit OK, and there it is. So after all that Babylon I just did, that was the result. Okay, that's a new part. Still not saved. Okay, if I go to my folder, okay, got the springs there, but I don't have anything else there. If I want to, I could do it, I could show it to you. If I hit save here, it's gonna save the work part, which is the bold one, which is the assembly, and any components in it. So if I save it, now I go back, there they are, they're stored. Okay. You do want everything in the same folder when you're doing this. It doesn't have to be technically, but it makes life a lot easier for you. Alright. So there's my new part, it's empty. I did tell you that when you make a new part with a model file, it comes with a CSIS. But it's a good time to remind you. Remember, when you're looking at parts in an assembly, like this, there's a filter on the parts. The filter usually by default is called the model filter, which doesn't show it only shows the finished bodies. So you won't see wireframe or sketches or CSIS or plane, right? Remember the filter? Right click, it's called a reference set. It's on model. If I set it to entire part, then I do see the CSIS. So that part does have a CSIS in it. It just wasn't shown by default because the filter is called the model, which only shows solid bodies or in it. There's no solid bodies. And the last thing I wanted to mention, because it's good to remember this. Remember just like 5 minutes ago I said the top branch, even though it's called an assembly, it was just a part, it was just a cube. But as soon as you put a child component inside of it, now the system recognizes it. Yeah, that is an assembly. It's got children. It's got that little L box, right? So now that I've done that, I'll do the other ones real fast. I'm making more component parts. I should have done a copy and paste on the previous one because then I could just change the number a little bit. This is 1002. Oh, I should have copied and pasted it again. I can copy and paste it right there. Okay, hit okay, there it is. Go there again. Paste it, just change it to 3. So, you know, like I said, if you're doing the exercise, you would have been way past this already, but I'm just explaining all this. And then lastly, we'll do one more. And again, it's really for the 3, it's for the plate and the 3 gauge blocks that we're ultimately gonna create. All right? Okay, so there's my assembly with the 3 parts. All right? For the base plate, okay, I go into a little discussion here. The base plate, let me jump to the end. The base plate's gonna look like that. It's gonna have 6 holes, 3 pairs of holes back there for the blocks to be screwed onto the plate, okay? And then there's one hole in the front here, towards the front. That hole is, you know, it's a gauge. We're supposed to sit there, how many springs were there? What did I say, 30,000 springs? We're supposed to sit there and grab all those springs one at a time and see, is it the small diameter spring or the large diameter spring? The 3/4 inch one or the 1 inch? If it fits in this hole, it's a 3/4 inch diameter. If it doesn't fit in that hole, it's a 1 inch diameter. So then I know at least partly what bin is supposed to go in. We hold it underneath the blocks to see what height it is, right? We're doing it that way, figuring out which diameter and which block it fits under best. Then we know which bin to throw it in. So we gotta make, all we're gonna do is make the simple plate with 6 holes. Those are threaded holes. And then that hole is just a simple hole with smooth sides and a flat bottom, because it's not gonna accept a screw or a bolt or anything, it's just temporarily stick a spring in, right? I'm just gonna say something else while I was talking about that. Yeah, I'll get to that again. So we're gonna make that, and you know, our job really is to figure out, like I said, when you're a tool designer, you're trying to save money all the time. So do we already have a plate the right size? Or what size stock do we have? And, you know, we could pretend we see all these different sizes. We're just gonna say, well, we do have a plate that's 5 inches across. It comes in a long strip, it's 5 inches across, and it's 3/4 of an inch thick. We have that. We could cut it into pieces, right? And save, you know, we don't have to cut the whole thing out from a larger stock. It's just one long strip, we'll just cut it off at a certain distance. And we also, for the blocks, you know, this is all just a discussion. For the blocks, up here, you know, we're gonna put those 2 springs on it. And the spring, you know, that spring is about 1 inch in diameter. We're not, in reality, we'll never have 2 springs underneath one block at a time. If we're using this as a gauge, we're gonna just grab 1 spring at a time, stick it in that big hole, see if it fits, and then put it underneath one of those blocks, and then throw it in the bin. It's not gonna stay under that block. Well, you know, so the big diameter is 1 inch, so we need something a little bit, that fits kind of nice. These don't have to be exact sizes, but a 1 inch diameter spring needs to fit nicely underneath one of those blocks, okay? So we have stock blocks, and we happen to have one that's 2 inch by 2 inch. You know, we're pretending on this. So like this, 2 inch by 2 inch on a block. So why don't we use that instead of having to take some other material and cut it more and make it in a certain size? Well, no, we just got this one long strip that's 2 inches by 2 inches, and maybe it's a really long bar. We can cut it off in certain distances. Those distances would be this way. So we decide, you know what, that would work out good, because we can put the springs under those. 2 by 2 inch, yeah, that would work out great. So that's the first thing we come up with. Again, to save money, we already got stuff existing. They really push that. If you look at that, if you ever look in the textbook and read some of those manufacturing engineers' book, we're going to reference it a lot. But if you look through it, they talk about that all the time. You're supposed to first see if you got something that already works. You know, use that. Always use that. You're always trying to save money, do faster. Well, so that's what we do. Okay. So 2 inch by 2 inch blocks. And then we have to think about, well, all right, we're going to stick them on here. So we don't want them too far apart, because even thinking about that gauge person, that spring sorting person, they got to sit there and they got to move their hand a certain distance. They even get into that. I mean, you could get into that with motion studies. How far do you think is comfortable to move your hand? You don't want to go farther than you have to. The less movement you have, the better. So if we have 2" by 2" blocks, we'll put them pretty close to each other. Maybe not right up against each other, but close, like so. And, you know, the hole right here, even where is that hole gonna be? Well, let's put it in the middle, because it's close to all three of them, right? Stuff like that you think about. So we think, all right, 2" right, and to keep, just to space them out a little bit, you know, and you could write all these calculations down in your head and come, you try to come up with good numbers, but also round numbers. So we say, all right, we'll take those 3 blocks, line them up like this. If we got about a 1/2 inch between each block and a 1/4 inch on the outside edges, yeah, we should be able to, we could then fit that on a 7.5 inch plate this way. Right? Again, it's not rocket science, it's just trying to make it fit in a decent way, right? Without too much trouble, something that's pretty round numbers. So that's what we decided. So, you know, I'll come back to that in a second. So it says we're gonna make the plate, it's gonna be 7.5 inches, but again, I'm jumping ahead here. On the block, as I showed you before, we're gonna use 2 screws to hold that block down to the plate. Okay, and by the way, even if you look in the book, you might look at those and you might say, those are bolts, aren't they? They're not screws. Well, there's actually an accepted definition of what's a screw versus a bolt. If something has threads on it and it gets turned into another piece, that's considered a screw. A bolt is something that you put a nut on the end of it. You might go all the way through a piece and then you put nuts on one end or the other. It's not written, don't really have to say it that way, but that's the generally accepted description. So we're gonna be using what they call screws because the end of the screw with the thread on it is actually screwing itself into a threaded hole in a part. There's no bolts on the other end, okay? So even looking at that, we're trying to come up with, well, what are some common screw sizes we have? And yeah, after a lot of talking and discussion and whatnot, you can read through it. We're using, they call them M8 by 125 because they're very common. M8, that's metric. That means the diameter of the screw is 8 millimeters. Okay. The 1.25, we're not going to really deal with that here, but that's the pitch of the threads. Okay, it has to do with the pitch, the angle of the pitch of the threads. Doesn't really matter much in what we're calculating right now, but the diameter does. 8 mil diameter, and that's where that's the smaller hole in the bottom of the counter bore here. 8 millimeter. Now the length of the screw, we're going to have to know about that, but we're not designing the blocks today, so I don't really care about the length of the screw just yet. Ultimately, we will, because you need to know how far you got to drill the counter bore holes and hold these blocks on the plate. So we're just saying we already decided because the parts 2 inches across, 8 millimeter diameter screws, we could space those out pretty nicely, pretty evenly in that 2 inch across distance. They won't be too close to the edge. They won't be too close to each other in the middle. They won't be too close to the back edge. And as far as terminology, when we do make the blocks, I'm gonna consider this the back of the block. So over here, this is the front. So this is one side and that's the other side. And I was even talking to my machine tool guys when I was writing some of this up. I said, is there a real specific formula for how you space those? And they go, nah, you can look at this and you say, try to keep round numbers if you can. So if we have 1 inch between them this way, between the center lines here, and it's 2 inches all together, that means we're gonna have 1/2 inch from the hole to the outside edge of that, and 1/2 inch from the hole to the other side. And to keep them centered this way, we're also gonna go 1/2 inch from the back edge. You might think, well, what does it matter right now? Well, we're gonna use those numbers to put holes in the plate. Okay, so when I get down, I'll come back and do this, but that's how these numbers came up. Well, yeah, I'll explain it now, and I'll show it to you. So see these numbers? Those are based on everything I just talked about. So the block is gonna sit right here. We're making the plate, but the block's gonna sit right here. Remember how I already showed you, but we're gonna have a 1/4 inch, I think I said that, 1/4 inch from the edge of the block, right here. So a 1/4 inch from here, then I got the block, and in the blocks here, the screws are gonna be here. So we got that 1/4 inch, and then remember I said the hole is gonna be a 1/2 inch from that side, and a half inch from that side, and 1 inch in between them. So using all that down here, right, okay, so 1/4 inch, and then a half inch to the first hole, right there. It says 19.05, but that's 3/4 of an inch from the side edge of the plate. But again, the block would be right here, but we don't have a block right now. Okay? And then you go an inch between them, because that's what I said. And then in this direction, it's the same thing. It's a half inch from the back of the block, but the back of the block is gonna be a 1/4 inch from the back of the plate. So the points, these are the 2 points for the holes. They're, whatever that millimeter is, that's 3/4 of an inch, 19.05 millimeters, right? So I just wanna get that out of the way, because I was talking about thinking this through, thinking about where things are gonna be. To actually make the holes, how we're gonna do this. You could do it right now with everything I told you. But there's a couple little things I wanna talk about. We're gonna make a threaded hole. Well, actually, no, I forgot to make, I gotta make the plate. I won't go past that stuff. But this is a good point, is I need to talk about this. It says make the plate component, so we're gonna make a sketch in the 1001, that's the plate, okay? I'll go to the part navigator. It says, make that on the XY plane of the existing CSIS. And as I always say, when you're looking at my instructions, and for example, I show you the sketch, look at where the red and green sketch vertical and horizontal axes are, right? They're on that corner there, which is really where the CSIS is. So we're building the part, saying the anchor of our part is the absolute origin of our part is down here in the bottom left corner of the plate. So in other words, if you make a sketch, and I used on path last time, as a reminder, I'll say this one more time. I mean, we did it last week, but in case you're on a different machine or something, remember, go to the early access feature, look at that guy down there, make sure that, use the new solver and user interface for sketching, make sure it's off. Okay? So I'm gonna make a sketch on the XY plane, not on path. I used that for my helix last week, I made that circle, and then we made a sketch on the edge of the curve. Also, by the way, if you're doing this and you see those 3 planes there, I don't like to see them, I don't ever really use them. So you can turn them off, they're just annoying to me. Show principal planes. You leave them on, it's not perfect. So I'm in the sketch, and then we're gonna make the rectangle. And I can see it's roughly, well, it's 190 by 127. Remember, we're in a millimeter model. I'm gonna start my rectangle. You could do a profile, I guess. So, I'll zoom in a little bit. So, with the column width. That's the width. The width, it should be like 190, what did I just say? 190 and 127, so. You don't have to be exact. That's close enough right there, right? There's my rectangle, okay? Now here's the thing I wanted to make sure I talked about, as I say here. It's gonna be 7 inches by 5 inches. The model's in millimeters, but our sheeting books and all that stuff and all the drawings we might be looking at, it's all in inches. Manufacturing world, a lot of it's in inches. Not everything, but it depends on where. Aerospace and automotive is different, things like that. You might work somewhere that they do use inches, you might work somewhere that they use millimeters. But 1 inch is 25.4 millimeters. So I tell you right here, key a formula to convert the value. So if you want to make this 7.5 inches, you can go to the, you can bring up a calculator and type that in if you want. 25.4 times 7.5, 190.5, so 190.5 millimeters. And then when you go to make your dimension here, if I make a linear dimension, I can do that. I can say from here to here, type in 190.5, okay? Or you could actually go to the field. When you place it, you can go to that field down here and type in 25.4 times 7.5. Okay, you can do that. But I want to show you what I think is a really cool way. Either way, it doesn't matter. I don't care how you do it. But right here, it's millimeters, right? But if you type in 7.5 IN, like that, I don't know if it's uppercase, well, I have my keys, well, let's see, if I do uppercase. See what it did? 190.5. No, if you just put IN after it, you can convert it on the fly. Saves you a lot of time, right? So there's one, it's already, that one's good, I'll make another one. It's asking me to start the first object for the second one. I'll go from the bottom to the top, I said that was gonna be 5 inches. I'll type in 5 IN. Okay. Now you notice it doesn't say 5 inches in there, even if I hit enter and all that, but once you finish it, out here it shows you millimeters. Okay, now if I go to double click it, see that, it does say 127 millimeters, but it knows, when it's gray like that, it knows there was a little formula involved, just a conversion formula. It does say, you typed in 5 inches. Okay, good to know that. Try this, I want to see. They didn't even remember that I used uppercase IN on my first one. I didn't remember that. But anyway, there's our plate. And see, I'm explaining things. If you were just doing this, read the instructions, you might be done already. You just have to wait for me to finish talking, right? So there's that part of it. Then we're gonna extrude that sketch, end distance of 3/4 of an inch. You can guess how to do that, right? Remember, good habit to use feature curves when you're picking sketches and things like that. I'll type in 0.75 inches, 3/4 of an inch. Right, there's the plate. And I don't know, I think if I, just FYI, see it still says 0.75 inches there, but I think if you do the show result and come back, see now it shows the number. 19.05 inches. Anyway, so there's that. And then, because I already spent all the time talking about this, I don't have to redo it again. We're gonna make holes. So, we're gonna make threaded holes. I don't know if you recall, but just like with CATIA, holes in holes in CAD, they have sketches. Well, if you create a hole brand new, it's all based on a point, right? It knows holes are round. Holes are always round and they're always centered on a point. They're always positioned with points. Those points can actually be wireframe points or vertexes or something like that. But they also can be sketches, and we're gonna do it that way. Okay? So I'm gonna go to the hole command. And even this, you can go into the textbook and look up a lot of this information for things like threaded hole. Okay? Now we're gonna make a hole that goes all the way through this plate, and the threads go all the way from the top to the bottom. You can actually have the threads only go so far if you want. But we're gonna say, let's keep it simple. We'll let the threads go all the way from the top to the bottom. The screw won't be able to go all the way through if it's going through the block, and the block has a counterboard, and there's a little ledge in there, and it's gonna stop. We wanna make sure it stops when it's that correct thread engagement. But what we're gonna use is something called metric course. Metric course lets us pick sizes like this. See how they have that M? They all have that M in front of it. That's what metric lets us do. So that's the kind of screw we have. We have the M8 by 125. Metric course means it's kind of a rougher, a bigger thread. Metric fine it's finer thread. Just to let you know, it doesn't matter what on our exercise. Metric course, it's a more common one. It's cheaper. So why not use it? We have a bunch of M8 by 125. Those are metric course screws. In fact, if I go to metric fine, there isn't any M8 by 1.25. There's an M8 by 1, but it's not M8 by 1.25. That's a metric course type of screw. So, and again, when you go there, don't be misled, because it looks like it went back to the one I wanted, but it says M1. So when you change that, it's going to go back to a different one on the list. So you got to make sure you find M8 by 125. We decided we got a lot of those. We're going to use those. Okay. There is something called radial engage. That has to do with, a threaded hole right here, a big hole. Let's say it was threaded. Well, if you look at it really close, somewhere is where the thread starts on there, and I think the radial engage has to do with that. Like, where is it along the part? Doesn't really matter for what we're doing. I'm going to talk about this just for a second. The tap drill diameter, well, that really means our screw diameter is M8, it's 8 millimeters. But with the thread and everything, it's the inside of the threads are not quite 8 millimeters, right? For an M8 metric course screw, there's like a formula, but there's a standard number you fit that in. And see right here, it's gray, it says tap drill diameter. It says 6.8, okay? Well, I said the the screw diameter is 8, but they're saying with the threads inside, it's 6.8. Just so you know, watch, if I pick a different screw again, or no, if I say, let's do metric fine, yeah, I'll try that. I'll do the M8, now it's not exactly the same screw, but it's M8, and see for that one, it's 7 tap drill diameter. So the fine size is closer to the actual head size, or the diameter, head diameter. I know you might be going, I don't know what you're talking about there, but it's stuff, if you work in this business, you will learn all that, you will know all that stuff, even without thinking about it. So, we're gonna say metric course, M8 by 1.25. That number is calculated on its own. There is, I don't think I have it in this document, I have some notes and things where there's a chart where it says, yeah, M8 screws, the tap diameter is usually 6.8 or 6.9, this one calculated at 6.8. Now the thread depth, okay, that's where I said you can have the thread just go a certain depth if you want. We want it to go all the way through, so we're just gonna say full, right? It's gonna be right-handed, so it's full thread depth. That's for the thread. However deep the hole is, the thread's gonna go all the whole depth of the hole, the entire depth of the hole. Okay, it's gonna be right-handed. It mentions, I don't show it, but it mentions we don't want to have chamfers where the hole starts or stops. They'll just be flat on the top. So turn those off. Open up chamfer there, turn off start, and then chamfer. I'll get to the position in a second. Hole direction, yeah, it's going to be normal to face. That's typically when you pick a face, it's going to put a point on the face, and the direction of the center line of the hole will be normal to that face you picked, which top face we want it to be normal. That's good. And then here is the actual depth limit. Don't get confused by thread depth and depth limit. The depth limit is the entire hole. The thread may or may not go down the entire hole. We are, instead of the full. So that's gonna go through the body, and yes, we're gonna subtract it. And in my instructions, I tell you to pick right about there, somewhere in the back corner. Because remember, when you make holes, another reminder, when you're making holes, it's looking for a point, but it's also thinking, if you're on a planar surface, it's thinking you wanna create that point with a sketch. And we do. If I had a real point out there, I could pick it, but whenever you see that, that means, you know, that blue plane and those red, green, and blue things, that means it's thinking, you wanna make a sketch there, don't you? Now, if you come down here, it's gonna go to the nearest vertex and place the origin of your sketch. I have you go to this upper corner, right about there, I'm just eyeballing it, and I click on it, okay? When I clicked on it, it knows the origin of the sketch was right here, and it's really measuring, not the edges of the part, it's measuring to the sketch or axis and so on, those points. Now those points aren't what I want, it's just where I happen to click. I could hit OK, and then do the same thing to make the second hole, but just because we can, I don't know if you remember this, making holes in X, CATIA too. You can make one single hole feature with 2 points in it, or 10 points in it. I'm gonna make 2, so I'm gonna go right about here, I'm just kinda eyeballing it. So I have 2 of them, and again, the numbers that are right there, they're not exact, but I'm gonna make them exact now. So I'm gonna go here, remember this takes you actually into the sketch. When you go into the sketch, see, that's where the sketch origin is right there, okay? And these measurements, for the 2 points that I picked, it just put them wherever I clicked. So that point, it's 16.4 millimeters from the X, and 16.9 from the Y. But that's not what we calculated, right? So what we calculated is this. So 19.05, 19.05, or you want to do it that way that I said was cool. And actually this time, sometimes it doesn't do it like this. Oh no, it didn't do it exactly like that. See this one right here? I don't want to use that one. You could use that one. But I wanted to call it out by having a 1 inch in between these two. You could do it this way, you could say, well, have that number and then add another inch to it, that would be that one. But I'm gonna delete that one, because I tell you to make separate dimensions. So this one, as I said, what did I just say? 3/4 of an inch. So I'm gonna double click with 3/4 of an inch, that's 0.75 IM. Does that work out to be 19.0 or 05? I don't know, looks like it's only showing one decimal place. You could change, I know it's 19.05 is correct. You could change the way it's displayed. For my instructions, I changed the format of the graphics in Sketcher so everything's horizontal, but it's 19.05. I can do the same thing here. 0.75 inches. Okay. Close that one. While I'm at it, I'll do that one. That's also 0.75. And then I said the distance between the two of them. I have to make a new linear dimension because I deleted the one that was there. That is, I know it's 25.4, but you could even type in 1 IM. Like that. So 25.4. So again, I'm telling you this and explaining it, so it's taking me a while. If you're ignoring me and just doing it, you might be done with it. So, finish the sketch. Okay. Remember we used, it comes back here and just double check. I could add more points if I wanted, but I'll just give it okay. And it shows those little dashed blue lines. Those are where the threads are. In fact, let me do this real quick. If I go to analysis, measure, that radius, it says 3.4. What's the diameter? 6.8. Remember what I said? The tap diameter, the inside of it, really, where the inside of the threads are, it's 6.8. It's for an 8 millimeter diameter screw, but the threads, some of the threads are outer and some of them are inner. That's really interesting. Those blue circles let you know that that's a tap. I'm sorry, it's a threaded hole. Okay, those are actually good. When we go to make the drawing of this later on, it's kind of cool. It knows that those are holes. Right? So we got that. And then with some more calculation, we basically say, well, remember there's 3 blocks and they're going to be half inch in between each one. So the way I'm looking at it is that set of holes, we're just going to save time, do a pattern of those 2 holes. So I got 2 holes sitting right here. When I go to make the pattern, it's going to start with them right in the middle of those 2 holes. So how far is it from the middle of this to the middle of that? Well, let's see. This is a 2-inch block, so that's 1 inch to there, and then that's a 1/2 inch, and then it was a 1/2 inch to the middle of the block again. Right? So, oh no, I'm sorry. So it's 1 inch to here, 1/2 inch there, and then 1/4 inch, right? Whatever it is. No, my brain hurts. But I have it right here. It says here, remember, each block is 2 inches in width. Each set of holes is 2.5 inches from the previous set. So from the middle of this block, the middle of the next block is 2.5 inches. So, we do a pattern. Okay? We're gonna go to Home tab. It's a pattern feature, not pattern geometry, the pattern feature. It's gonna be a linear pattern. I'm gonna reset the window. It was on general, it must be the last count pattern. Okay? What we're gonna pattern it, and this is where it's kind of handy that hole that I made, and I forgot to say this. See how it calls it out in the navigator? It actually says M8 by 125 threaded hole. I didn't name it. That's what it named it. It even shows kind of a threaded hole graphic there. But that hole consists of both of those. So I only have to click on one feature. Okay. For the vector direction, what do I tell you? Okay. It says use the x-axis. That's good. That's a good habit actually. For the vector direction, it's a good habit to use the CSIS. You could use an edge, it would work here, but a best practice in all of NX is try not to use edges if you can use something else. I might wait for my 3 dots there, pick the x-axis of the data coordinate system. Okay. And then we're gonna have, I know that's one set, I'm gonna have 2 more sets. So remember the count includes the original, so I'm gonna make it 3, and And the pitch distance, what did I say it was? 2.5. 2.5, so 2.5 IN. See, it's going from the center to the center to the center. And because, just as a reminder of the way patterns work, see, that's why I talk about this, I want to remind you of things. When I made that hole, it came with a built-in Boolean of subtracting itself. So when you pattern the hole, the new ones also subtract themselves. If you had a cylinder and then a subtract operation, and you pattern just the cylinder, it wouldn't pattern the subtract. You could actually pattern a subtract too. Anyway, they were subtracted because the original holes were subtracted, right? So there's that. And then we're gonna make one more hole, and I go into this really long paragraph, I already kind of talked about it. We're gonna put it in a nice spot where you don't have to reach too far, and it's kind of in the middle of all the other ones. And we wanna make it big enough for the small one to fit in, but we don't wanna make it exact, because you know, you could take it's a 3/4 inch outer diameter, right? If you make it exactly 3/4 inch, we'd have to line it up just exactly right, maybe push down on it to get it in there. We're gonna make it so it's kind of easy to put a 3/4 inch diameter in there. So we calculate that 21 millimeters, that's good. Okay? Because I think 3/4 is 19.05, so give us a couple extra millimeters. And there's no way that a 1 inch diameter would fit in there. So we want it to fit the small one in there easily, the large one won't fit. Okay? As far as the depth, even that, you know, you could think about it, talk about it. Well, you can make it deep, but if you make it deep, then doing a little motion study, you might stick the spring in there, and if it goes in there, it's going in there nice and deep, then you gotta take it, extra work to get it out again. If you just make it relatively shallow, you know, all these little things is what you really be thinking about as you're doing this. So we just decided, after all that, the depth of the hole will be 10 millimeters. We'll make it 20 millimeters in diameter. And then it says, well, we'll put it in a spot that's nice and round numbers, 1 inch from the front of the plate, and exactly half the length of the plate. Okay? So how do we do that? Well, it's a hole. But this is not a threaded hole, this is a simple hole. And a simple hole actually comes with a point down at the bottom, right? It's got a, oh, because it's through body. We're gonna do a depth, we're gonna have a value here, okay? You know, a drill bit that's drilling a hole, it has a point, it comes to a point, right? Now, when a hole goes all the way through, there's obviously a point there. But by default, you can even see it on this hole right down here. There is a little, oh, it's hard to see because it's so long, but there's a point on the bottom of it. Can you see it there? I guess you can see it there. There's a point. But the hole I want to make is going to go only part way through, so there will be a bottom on the solid, and we want it to be flat. So it says depth to shoulder, or not depth, you can say, oh, there's an angle. There's an angle of that point on the bottom. If you make the angle, what is that, 0, 180, I forget, 0. If you make the angle 0, then there's no point on the bottom of there. Sort of tell. You'll see when we make a hole. It's flat on the bottom, right? So let's see, I'm gonna make this kind of similar to what I did before. It's a simple hole, right about there. Okay, 21 millimeter diameter, right? But it's not going through the part. The depth is going to have a value, and I think I said 10. After all the thinking, I can't remember what I said. Maybe 10? Okay. And then, again, it's because I picked a planar face, it's saying, well, you're making a sketch. So I make the sketch. Okay, it gave me, I wasn't really paying attention when I made the sketch. It looks like it lined it up. The origin of the sketch, the closest vertex I found was up there. You know what, I don't want to do that. I'm gonna actually get out of this. I'm gonna undo that. Cancel that. I should have done it like this. I should have went to hole command. Of course, now remembers everything I had before. Simple hole. Value for the depth. 0. Give me the angle of the tip. And I want to make it so that, see how my cursor is over here somewhere? So I'm going to make it like that. so that the origin of the sketch will be over here. I want it there, I don't want it in the middle of some hole in the middle of nowhere, okay? So I'll also make this a 21 mil diameter, and then I'll go into the sketch itself, that little button. And it does have the right dimension types, you just have to adjust this. And you can even do a, well, 7.5. You can do a 7.5 inch divided by 2, I think, 7.5 IN/2. Calculate, so it's halfway that way. It's amazing how many calculations you can just have it before you. And then this one, I said we're gonna make that 1 inch from the edge. So that should put the hole right where I want it. I'll close that. Finish that. Oops. Remember that little issue, if you're trying to rotate the zoom and sometimes there's a window open, it closes the window for you. I thought I changed this, oh, I changed it, I didn't change the 50. It's F50, I want it to be 10. And go back and edit. There we go. Okay. So that is the last step. Most of it's just NX stuff, but also, I mean, it's good. We talked about tooling kind of concepts, right? What the things you're gonna be thinking about. And there is a lot of that in tooling. A lot of measuring and calculating. Not having deep calculus stuff, but numbers and conversions and all kinds of things like that. And you're gonna learn more about screws and bolts and the different standards. Everything's really important. And that, I'm telling you, that textbook, it's got everything you can imagine. I'm also gonna, not this week, but coming up, there's a couple of videos that the other instructor used to use, and I looked at them, and they're pretty good. If you go on the internet, go to YouTube, you can find anything you wanna know about any of this tooling stuff. People make videos. I mean, you don't need this class, you should just go look on YouTube and you learn everything in videos, because you actually see their machines working there too. Here, I'm just talking about it. Anyway, that's the assignment. You will turn that in. So you'll have an assembly. Let me save this. And I'm gonna save everything I did, right? So the best way to save it, I've got an assembly with one part that has geometry and 3 parts that have nothing in it yet. If I double click on the top and make it the work part, and then I go up here to this guy called save, it says to save the work part and any modified components, so we'll save everything. Okay. And I was gonna say, because that's not the work part anymore, it's got the model filter on it, so I don't see any wire. I do still see the threads, the blue, but I don't see my sketch, I don't see the CSIS. I'll look at my folder once again. Now I've got the springs I had from last week, and then I got those 4. The assembly and the 3 parts. So turn in, all you need to turn in for this one is the assembly and the 3 parts. You don't have to turn in the springs again. You guys did some really good jobs with the springs. I was really proud of the ones I saw.
Thanks.
Question?
I'm enjoying the easiness right now. Is it gonna ramp up later?
What? You thought that was easy? Yeah, there's more to it.
Yeah.